In the last video, we considered one-dimensional heat conduction and assumed that heat conduction in other directions to be negligible. However, this is not always the case, and sometimes we need to consider heat transfer in other directions as well. So in this lecture, we're going to extend the equations we developed last lecture to three dimensions in rectangular, cylindrical, and spherical coordinates. So for rectangular coordinates, they are functions of x, y, z, and t. So it's fairly easy to extend the one-dimensional case we had in the last lecture just by adding two additional terms. And so again, if in steady state, the right-hand side is 0, this is referred to as Poisson's equation. And you see this equation in various other physics and engineering courses. For example, you see this in E&M and also in fluid flow and all kinds of other subjects. These equations just keep popping up. Now, if it's transient no heat generation, then this term is 0 here, and so it reduces down to this equation, which is what's known as the diffusion equation. And finally, if both of those terms are 0, it reduces down to this equation, which is Laplace's equation. And again, you see this equation in E&M. If you take that course, and I'm sure you all do at some point in your career. For cylindrical coordinates, they're functions of r, phi, z, and t. So again, we add two additional terms to take into account the angular dependence and the z dependence. We can also define what's known as the heat flux components for the radial, the phi, and the z directions. And finally, for spherical coordinates, again, we add two additional terms, and we define the heat flux components in the r, theta, and phi directions as shown. So let's take a look at an example. Heat conduction in a short cylinder. So a short cylinder of radius r and height h is heated in an oven to approximately 600 degrees Fahrenheit, and then taken out of the oven and allowed to cool at an ambient air temperature of 65 degrees Fahrenheit. Assuming it's cooled uniformly and all outer surfaces and the variation of the thermal conductivity of the material is negligible. So in other words, we have a constant K throughout the material. We want to obtain the differential equation that describes the variation of the temperature during this cooling process. So here's shows the short spherical billet, as he calls it, metal billet. So it's initially at a uniform temperature, and we're told that it's heated up and then taken out of the heater. So it's not undergoing any heat generation inside of it, so E dot gen is going to be 0. We're also told that it has no angular dependence, no phi dependence, because we're told it's cooled uniformly from the top and bottom surfaces. So therefore, the temperature is only a function of the radial and the z and time. So therefore, our equation, general equation, which is here, we can eliminate the phi term, and we can eliminate the E gen term, and so we can write our equation as shown here. Now, since the K is constant, we can take it outside the derivative and divide through by it, and again, it reduces down to this equation here finally, where we define alpha as the thermal diffusivity of the material. So here's our final equation that we would have to solve. Given the boundary conditions, we could solve this